we're good then? All right. Great. Okay, good. Yeah, so today we have Thanaporn coming all the way from Tokyo to tell us about wavelike dark matter. Take it away.
Okay. Good afternoon, everyone, and thank you for having me here, and also for the introduction. My name is Thanaporn Sichanugrist, and today I would like to talk about the direct detections of dark matter, especially wavelike dark matter, by using superconducting qubits, the type called transmon, and also some extensions of using quantum circuit to improve the signal. So my talk would be based on these three papers. So for example, the first one is talking about hidden photon search using transmon qubit. The second one talk about using quantum circuit to improve the signal. And the third one, the most recent one, talking about axion search using qubit. So the collaborators of this work are 6 people. So Shion Chen-san, Hajime Fukuda, Toshiaki Nada, Takeo Mori, Tatsumi, Nita, and me, Thanaporn Sichanugrist. Okay, so let's start. So in this talk, I will give you a theoretical framework of the direct detection of qubits with the effect of dark matter. Okay, let's see. First, as a background motivation, I think we have several times heard about qubits. It's a quantum two-level system developed for quantum computation. For example, we have 0 state here and first state here, and we have some energy gap between them. This kind of system can physically realize, for example, through ion trap system by molecule NMR system, NV center, quantum dot, photons, or superconducting qubits, or superconducting system. So in our case today, we will focus on this one and the spatial type so-called transmon. And because it is developed to be a part of quantum computation, in the same time it develops some properties that it's also a good thing to be a quantum sensor. For example, we can precisely read out its state. Also, we can control its state. For example, we can set its state, not just 0 or 1. We can set the superpositions of state between 0 and 1 as well. And in some types of qubit, we can even tune the gap of the system. The other thing is that we can group or maybe use not just one qubit. We can entangle many of the qubits. And this can help the enhancement of the signal as well. The other thing I should talk about is the target that we are aiming. We are aiming the so-called wavelike dark matter. Those are dark matter which mass much smaller than 1 electron volt. In that case, to satisfy the observed dark matter energy density, the number of the particle inside the de Broglie wavelength should be enormous. So the density is large in that de Broglie length. So approximately in simple estimation, you can treat this kind of dark matter as classical wave. So that's why we call it wave-like dark matter. And the candidate we will focus on here, for example, dark photon dark matter and axion dark matter. For the hidden photon, we can have this kind of kinetic mixing. E is the electric field, ordinary one, and E prime is for the electric field from the hidden photon, or the hidden electric field. By this kinetic mixing, the hidden photon can convert to the ordinary photon, which is visible, and can become a signal that we can detect. For the case of axion, we have this kind of Chern-Simons term, Ga gamma gamma, axion field A, electric field, and B, magnetic field. In this case, when we apply static magnetic field, through this coupling, axion can convert to electric field. These electric fields, or the induced electric field by the dark matter, is measurable by superconducting qubits that we are going to talk about. And because we have limited time, so in the talk, I will just focus on the axion case. Okay. So before going into detail, I would like to give you some rough picture of the mechanisms that we will use. So for example, we assume in the presence of axion dark matter, and we assume, and also in the setup, we also have the transmon qubit. When axion oscillate through the background of magnetic field, it can become electric field. And in the case that mass of axions is the same as the omega or the energy gap of the qubit, it can induce the state transitions of the transmon qubit from ground to excited state. And this excitation we can identify as a signal of dark matter. So the outline of this talk is that first I will give an explanation about electric field signal induced by axion dark matter in the shielding cavity, because we want to put shielding cavity to shield out any non-necessary electric field noise from outside. And the second part, I will talk about signal detection by using the transmon superconducting qubit itself. The third part would be the extension that we can use quantum circuit to improve the scaling of the signal with respect to the numbers of qubits in use. Okay. So first, let's go to the axion dark matter. The model that we are thinking about is this one. So we have first the terms for the electromagnetic waves, the terms of the axions and its mass, determined by ma squared here. So its mass is ma. And the Chern-Simons interactions. So we have Ga gamma gamma as coupling, and A is axion field. So we have it coupling to the E dot B. So in the presence of B0, which is magnetic field, axion can convert to this electric field, which we want to detect as a signal of dark matter. And we also treat axions as a dark matter. So the one that we focus, like I mentioned at the introduction, we want mass it to be much smaller than 1 electron volt. And in a simple estimation, we treat it as a classical wave. So for example, we have axions field here, 8e, which oscillates by the frequency determined by its mass, ma. Amplitudes are determined by A0. And this alpha is the phase of the dark matter, which is a kind of random but constant within some coherence time scale. And we also require that axions compose as a whole of dark matter. So we require the observed local dark matter energy density to be equal to ma squared A0 squared. Okay, let's see what's happened if we have shielding cavity and axion background. So first, if I spoil you, as a result, axion can induce electric field inside this shielding cavity when we apply magnetic field B0. We can derive this equation of motion by that Lagrangian to have something like this. So the left-hand side is the usual things. You have electric field E here, nabla square, and time derivative square. And in the right-hand side, we have source of the generations of the electric field. So we have A0, we have the oscillation determined by ma, and also magnetic field B0 here. We also have the usual boundary condition, which is that electric field parallel to the boundary equal to 0. So based on this equation of motion and boundary condition, we can solve for its solution, which is this red one. So it oscillates with the frequency ma as the source, and its amplitude is written here. Depends on Ga gamma gamma, the coupling, and the field amplitudes of the axion A0, and also B0, which is magnetic field. And the other additional factor here, kappa, express the cavity effects, which roughly speaking, it shows the overlap between the source to every mode function of electric field inside. So it's the integration between the B0 and the mode function inside. And what I want to say is that kappa, typical value is a kind of order of 1, it can be 1. And it actually can be larger than 1 as well. So to show you an example, I just plot some graph to visualize things. If you have a background of axions, and also if you use cylindrical cavity as a shielding cavity. In this case, I just put some random number or the relation between MA and R, which is radius of the cavity, to be equal to 10. Is this just random number? You can put other numerical values. And here, when you put the magnetic field in the Z direction, you get this kind of profile. The color represents the values of kappa. What this thing say is that you have a peak of the signal at the middle of the cavity. And this peak, for in this example case, kappa can equal to 5, which is slightly larger than 1. It can be larger than 5 as well. It can be 10. It can be 100. But typical value is 1 if you didn't care about these things. Okay. So I've just explained about the electric field that induced by axion background in the shielding cavity. Next, I will introduce other characters in this story, which is our sensor, transmon qubit. For example, if you have this kind of sensor, what we would like to do, we will put our sensor in the middle of the cavity to sense the strongest signal. And okay, next I will talk about.
Are you treating the this electric field is induced by the axion?
That's right. That's right.
And then you're treating it as a classical field.
Classical electric field, you mean, as a result of, yes, that's right.
In reality, the axion coupling is very small. So these are really photons.
I would rather say if the axion source is in the, if you treat it as classical field at first, the induced electric field, if you say it in a quantum language, it would be in coherent states. So yeah, you can say the photon, but it's a superposition of 0 photon, 1 photon, 2 photon, with the amplitudes of that 1 photon is maybe small. But we can treat it as classical field, yeah. In technical terms, it becomes coherent state, I think. Okay. So yeah, if you have any questions, yeah, you can shoot me. Yeah, any question during the talk. Okay, next I will talk about the detail of the sensor that we would like to use. It's called transmon. It composed of 2 elements. The first one is the usual capacitor. So yeah, usual capacitor. And the other one is the so-called Josephson junction. It's nothing but the thin insulating layer sandwiched by 2 superconducting areas. And in those superconducting areas, electron couple to the so-called Cooper pair. And collectively, we can express electrons wave function as one wave function. For example, in the left side, we can express it by psi1 with phase phi1. And the other side, psi2 with phase phi2. And the interesting thing is that the difference of the phase, for example, phi1 and phi2, the difference between them is the dynamical variable of this system. Its dynamical quantity in the system. So for example, in your Hamiltonian, you have these 2 terms. First is term for the energy of your capacitor, so just Q square over 2 capacitance. And for the second term, it the terms from the tunneling energy of the Cooper pair through this thin insulating layer. The constant determined by EJ. And this dynamical quantity zeta is the difference of the phase between the 2 superconducting areas. Okay, I will tell you the other important thing is that this Q and zeta are actually conjugate variables to each other. So you can treat, for example, zeta as generalized coordinate, and you treat Q as momentum. You can do something like this. So this term is nothing but the cosine potential of your system. And this thing is just your kinetic potential. And by that, you can also quantize your system regarding these 2 as conjugate variables. And when you just focus on the two lowest energy state and write the matrix elements of your Hamiltonian, just focus on that two lowest energy state, you get something like this. So you just get the energy gap of your excited state with the energy gap determined by the constant Ej over the capacitance. But as a whole, the energy level is something like this because your potential is not just zeta squared, it's cosine potential. So you have anharmonicity, which means that the energy between those states are not the same. In the LC case, in the usual LC circuit, you will have, for example, the quadratic potential which gives you the harmonic oscillator. In this case, the story is a little bit different. So you have the energy gap between those states are not the same. And because of that, for example, you can input microwave with frequency equal to omega. In that case, it will induce the state transition between ground and excited state, but not the transition between other states. If we tune our microwave with frequency equal to this gap. So that's why we can just focus on the two lowest states and treat it as a qubit. Okay. And in the presence of electric field induced by axions that we have already discussed, it can induce the voltage difference across the capacitor. So if the voltage difference would be something like this, it's just the electric field multiplied by the distance between the capacitor plate. So you have additional energy to your system, which is charge multiplied by the voltage difference. And as I have said, Q is one of the dynamical quantity. So when you write it down in terms of your two lowest energy state, which is ground excited state, you get some matrix elements of your Hamiltonian, like these two lines. The first line is the energy of the excited state. And the second line comes from the interaction Hamiltonian, which is this thing. So what is this thing? It's determined by first, the zeta, which is the effective coupling constant. This zeta depends on several things. First, it depends on omega, and surely it depends on capacitor, because the interaction that we utilize here is the interaction between electric field and nothing but capacitor. So it depends on capacitance, and it also depends on the distance and also the amplitudes of that electric field induced by axions. It also depends on the direction, the angle between the induced electric field and the z direction, but that would be fine because we can, in reality, apply the static magnetic field in this direction. That would give you the induced electric field in the same direction, which is the case that your capital zeta becomes to 0. So you can just neglect this angle. Okay, and next, when you have this Hamiltonian, what does this thing say to you? First, in the presence of zeta or in the presence of non-zero axion background, it can induce the state transition between ground to excited state or excited state to ground state. And you can, based on this Hamiltonian, write the Schrodinger equation. We will focus on the case that mass of axion equal to the band of to the energy gap of the qubit, or we require MA to be equal to the omega. In that case, you can write Schrodinger equation like this in the interaction picture. So psi G is the amplitude of ground state. Psi E is the amplitude of excited state. So this thing say to you that in the presence of zeta, it induces the transfer of the amplitude between these two states. And the strength determined by the values of zeta. Okay. So here I thought show you some schematic or the example of the case. For example, when you initialize your qubit in ground state, this is the probability that you would observe your qubit as in excited state. So the probability will gradually grow. It's a tail of Rabi oscillation, but because the coupling is so small, you just see the tail of the whole oscillation. So it's gradually grow with this behavior. So the probability to observe excited state when you initialize your qubit in ground state is eta square tau square. The eta is the coupling and the tau is the time scale of the coherent properties. For example, it is determined by the operation times of the qubit, or the time scale that dark matter approximately behave like a coherent classical wave. And in the mass range of interest of our dark matter, which is around microelectron volt or 100 microelectron volt, the time scale is around 100 microseconds. And with the typical values of the transmons, for example, the capacitance of 0.1 picofarad, the distance between the capacitor around 100 micrometer, the magnetic field of 1 Tesla, and the coherence time scale of 100 microseconds, and with GA gamma around 10 to the power of minus 10, you would get 0.1 excitation rate, which is sizable value. So for example, if you do this 10 times, at least one time you get an excitation with this kind of effect. But of course, what we want to probe is the values much smaller than this, not just 10 to the power of minus 10. We want to probe something much smaller. So what we would like to do is to be something, for example, like this one. So we would like to prepare many qubits as we can. For example, in this case, we prepare it in ground state with NQ qubit. And then we let it evolve with the effect of dark matter with that coherence time scale tau. And then we measure to see if that qubit is excited or not. We then repeat it many times as you want and with the time that allowed you for each frequency bin. Why I say that? Because you can tune the energy gap of the qubit, which means you can change your sensitivity channel that you want to probe, that whether there is an axion in that frequency. So for example, for each frequency bin, you would get something like this as a signal, total signal of the qubits go from ground state to excited state. It's just number of repetitions that you do the experiments, the number of your qubits, and the probability that one qubit is excited, which is eta square tau square. And okay, when you tune, for example, let's say you tune the energy gap of the qubit from gigahertz to 10 gigahertz to cover this range. And if you're lucky enough that the mass of the axions equal to the some frequency that you're sweeping, you would get this resonance peak. The other value is just some background. So you can calculate the significance. For example, in the simple significant estimation, you just take the number of your signal compared to the fluctuations of your background.
What is your bandwidth?
The bandwidth is determined by the coherence time scale. So it's around inverse of this time. Yeah. Would be kilohertz, because we would probe around gigahertz. And if I say in a term of quality,
is very small.
Yes, that's right. Yes. Okay.
So it takes a long time to scan.
That's right. You're right. It also depends on how much time you use on each bin as well.
Right, but how does this compare to like ADMX?
Okay, so for example, this, if you turn into the quality factors, it would be around 10 to the power of 6, which is the same order as the ADMX, I guess. So the time would be the same order.
ADMX takes a long time to scan.
Sorry?
ADMX takes a long time to scan.
Yeah, yes, but we have different thing in the sense that in the qubit, in my understanding, we can tune the energy gap more convenient compared to the case of cavity. In the ADMX, you use cavity and you have to set the frequency of your cavity to compatible to your
How do you
sensitivity.
tune the energy gap?
Okay, that's very good question. So for example, this is the simple model of the transmon. It cannot tune your frequency if you just use this figure. To tune your frequency, instead of one Josephson junction, you use two Josephson junction. So you make it as a loop. In that case, this EJ will become effective EJ, which you can tune it by apply some magnetic flux through that loop. It's called, the technical term is called qubit. Yeah. Okay. And in comparison, if you want to tune the frequency of the cavity, I think it's take a lot more effort to tune it more compared to this.
But it's not really like how easy you tune, right? It's like how much time you need to integrate on each bit.
How much time?
Yeah, I think I don't know about ADMX, but I can imagine to spend a day or something to change the cavity property. But I think that it seems to me that the time really depends on how much time you need to observe in each frequency bit.
Okay.
To reach your target.
I will have some plot at the last stage to show you. For example, if we assume 1 year total of experiments, how much time we need for each bin to get those kind of sensitivity. But to answer your question right now, so to my knowledge, to change your frequency of the transmon when you put qubit in the replace of this, it's just you change the magnetic flux through this loop, which is the thing that not take time to do. You will have need some time to calibrate, but that will not take you too long. Okay. Okay. So, okay, about the background, I didn't say about the background yet. So there are several things to concern. First, about the thermal noise or thermal excitation. I need to say that it actually included in the definitions of the coherence timescale of the qubit. So for example, when you do some experiment to check your coherence timescale of the qubits, it's already taken into account the thermal effects of your environments of the qubits. So that would already include in the tau. So the noise here, P noise here, which is the rate of the noise per qubit per measurement, it's mainly from the qubit readout error, which is due to your measurement protocol. And also maybe due to some cosmic ray enter your shielding cavity. In the present time, the good values, the typical values that can be achieved by using transmon is around 0.1%. So for example, you measure 1,000 times, you would get a 1 time of false measurement result. Okay, this is the process of the measurement, a simple one. We want to do better. We want to, it's not a present time project, but this kind of thing needs more time to realize. What is it? We want to use some quantum circuit to entangle many qubits together to enhance the signal. This primary idea is you can find, for example, in the paper of Gio-Vannetti et al., which focus on atomic clocks and use some entanglement of atomic clocks to enhance the signal. And for the quantum circuit and entanglement for dark matter detection, you can find in our paper that discuss about using general qubits in quantum computer to do such a thing. And also the paper of the Ito et al. That come out just the day before our paper appeared in the arXiv that's focused on ion traps. Okay, so what I have told you previously is the left-hand side. So it's individual measurement. You initialize your qubits in ground state and you separately let it evolve and you measure it at a later time. Because you just separately do it. So of course, you would get the number of the signal linearly depends on your number of qubits. That should make sense. But we can do something different. We can do something that I will tell about the GHC preparation here. Is the name of the specific state, the entangled state. So we will do some operation, the quantum computation operation, to entangle those qubits before we let it evolve and check the results. In this case, you have to reinterpret your signal. I will tell you about this. But as a result, the number of the dark matter signal is not just linearly depends on the number of qubits, but the quadratic dependence on the NQ, which become NQ square here. Okay, so to understand about that, let us recall about the evolutions of the qubits under the effects of dark matter with the resonance condition. So we still require MA to be equal to omega within the bandwidth. So yes, you would get this kind of equation like I have already shown you. So we have the amplitudes of ground state, excited state, which can be transferred to each other by the presence of axion background. This data depends on the capacitance and depends on the axion amplitudes and also the magnetic field applied to your system. You can write it in terms of the unitary time evolution operator, which becomes something like this. The alpha here is the phase of the dark matter, which we don't know, and it's unknown. I will take into account that later, but first, for simplicity, let's assume that we know it, and we set alpha to be 0. In this case, interestingly, we have eigenstate of this unitary operator as plus minus state, which is the superposition between ground and excited state with the sign plus and minus here. So when you let this plus or minus state evolve, you will get this additional phase, which is e to the power of plus minus I eta tau. Depends on either you is a plus or minus state. And this is for just one qubit. Let's say you prepare NQ qubit state in this plus or minus state. Your phase will accumulate it coherently become something like this. E to the power of plus minus I NQ eta tau.
This is not the entangled state yet.
That's right. This is not entangled state yet, and this phase is global phase, so you cannot measure it. So what we would like to do is, we want to create the superposition state between this plus state and minus state, so that the evolved phase become, so to be precisely, the difference of that evolved phase become measurable. So to do that, I have some diversion, the quantum computation basic stuff put in these slides. What is quantum computation operator? Is just something that you manipulate, an operator with qubits that you manipulate its state. So for example, you can do qubit with adamant gate. It's called adamant gate. By applying this operation to your qubits, it can change your qubit ground state to plus state. It can change excited state to minus state, which plus and minus as positions of ground excited, as I have said. And you can do something like bit flip. It's called X gate. You change ground state to excited state. You change excited state to ground state. You can also have this C gate, which is, it's just X and C Pauli matrix. So in this C gate, you give additional minus phase to excited state. And in terms of plus minus basis, it's flip your plus to minus and minus to plus. These three are one qubit operators. You can also have something more sophisticated. You have 2 or multiple qubit gates. In this case, it's something that you decide what to do to the second qubit based on the state of your first qubit. So for example, if your first qubit in ground state, you do nothing to the second one. So it's I operators. But if your first qubit is in excited state, you do a bit flip to the second one. This is called C0 gate. For the control C gate, it's similar to the control NOT. You just replace bit flip to the C operator. And why I tell you this? Because you can combine those operators to create the so-called GHZ state, which is the superposition between plus and the minus state. This is entangled state. So for example, you can do by using this kind of circuits or this kind of circuits. They are not unique. You can create GHZ state by several ways. This is just an example that we show in our paper. So for example, you first prepare your qubits in ground state. You apply some other math gates to change your ground state to plus state. And you do some C naught or control C. Why you do some control C or control naught? Because this operator is entangled by its own sense. So you have to do something like control naught here, control naught here, control naught here, a sequence of control naught, or the control with multiple C gates to create such GHZ state. You can try to calculate this to see that it actually goes to the GHZ state. It's straightforward calculation. And what happens when you prepare this GHZ state? For example, you first have this kind of GHZ state, and you let it evolve under the assumption that alpha equal to 0, which is dark matter phase. For the plus state, you obtain this phase e to the power of I n q eta tau. And for the other one, you get the same amount of phase, but different sign. And right now, this is not just a global phase. So the difference of it is measurable. And by these ingredients, you will see that you will get the scaling by NQ square, not just NQ in your signal. Okay. So let's say you prepare GHZ state. And when you let it evolve, you have this plus and minus with the phase of the different sign. You can rewrite it in this way, which is the first term is nothing but your original state. It's nothing but original state because it's just plus, plus, minus. And the other term is the difference thing is plus, minus, minus state. You can see that if you assume there is no axion background, or in that case, eta would become 0. If you assume eta becomes 0, this term will vanish. You get just original state without any change. So you can see that by the presence of axion background that induce electric field interact with transmon, or in the presence of the eta non-zero, you would get this term. So you can identify it as dark matter signal in this case. So what is the difference between these two states? How can you differentiate it? How can you identify which is which? For example, the first one is actually the eigenstate of these products of C operator, which C is the Pauli C matrix. You can try to calculate and see that the eigenvalue is +1. The meaning of this eigenvalue +1 means if you measure all of the states, the state that is excited states becomes even number. For the other case, due to the sign difference here, the eigenvalues become -1. And when you measure all of the states, you will see that it gives just only the odd numbers of excitations of the qubits. So you can identify the difference by this. So in this case, if you identify the signal like this, you get the probability to observe the signal, which is the amplitudes before that state like this, sine square of the NQ eta tau. So by assuming that eta is small enough, which is small, because GA gamma is very small, you get this NQ square eta tau square. So now eta tau square is nothing but excitation probability of 1 qubit. So now it's not just NQ linearly, it's NQ square in the result. And this, I have to say to you, is just the case for when we assume alpha equal to 0. In the actual case, we don't know what the values of alpha is. We just know that alpha is some constant values up to some coherence time scale of dark matter in a simple approximation or in a simple estimation. So for example, when you do an experiment, repeat it many times, you will get the random values of alpha. So you can average it out. It will become 1/2. So still you get the same results in q square eta tau square. And next, this slide is the results. Okay. So it's the sensitivity projection plot when we want to probe axions. We have many things going on here, but first, the vertical lines is the coupling Ga gamma gamma. The horizontal line is the mass of axion. And the gray area is the constraints. For example, the dark gray area is the constraints from astrophysical observations, such as the cooling of the stars. And the light gray area is the constraints from the haloscope experiments that they use cavity resonance to probe the signal. And our projection is those of colorful contour. We have many colors here. So let's see what is these things. So first, the green one is those when we just assume cavity effects kappa equal to 1. So in this case, it's just typical value when we do not rely on any cavity effects. And the dark one, the dark contour is the projections for when you use 1 qubit. And the light green is for the 100 qubits case. So even though we assume just 1 or 100 qubits without take care anything about the cavity effects, we can probe the area over the astrophysical constraints. And in this case, okay, I forget to tell you that I assume the total measurement times of 1 year. And regarding the bandwidth, you will divide those range. For example, this is around 2 gigahertz to 20 gigahertz. You will divide those range by million bins. And each bins, because you want to take a total time of 1 year, we have time for each bin around 15 seconds. Which means that in these 15 seconds in each bin, you repeat many times as possible with these 15 seconds allowed. By each measurement time, you use time around our coherence time scale, which is around 100 microseconds. Okay. So next, we also assume magnetic fields of 5 Tesla. And the error rate per qubit per measurements cycle around 0.1%, which is a typical value we can obtain by the present time transmon. So like I have said, the green one is those from the 1 and 100 qubits. But if we also combine the cavity effects, just a bit of cavity effects, which we take kappa to be 100. In that case, you can improve your signal to go barely touch the case VC axion model. Again, the dark blue is for the 1 qubit and the light blue is for the 100 qubits. And if you also combine it with the entanglement through the quantum circuits, that give you the improved scaling, you can cover the area of the QCD axions model, including KSVC or DFSC axion model. So I would say that the green one is those that we can do an actual experiment in the present time, because the 100 qubits is something that we can achieve right now. And it requires money though. I mean, in principle, we can achieve 100 qubits. And for this case of kappa equal to 100, in this case, we also can do it. From now, it's reasonable in the present condition. The hard one is the entangle of 100 qubits, because...
What does it require to get the kappa equal to 100?
Okay, so for example, let's say that kappa is, you can estimate it as a quality factor. So when you use cavity and you set your cavity frequency equal to the signal frequency. In that case, you will use the full quality factor, which is, for example, 10 to the power of 6 or 10 to the power of 10 in the present time of cavity. In this case, you can take it as a kappa, as a quality factor, but we don't use the resonance condition. We just use the very tail of that resonance effect. So it's tell you how close the cavity frequency to your signal or to your qubit frequency. But the 100 is totally nothing compared to the 10 to the power of 10 of the cavity harrowscope experiments. So to say in other way, you need some overlap between your mode functions in the cavity shield with your signal, which is B0 of axions. Yeah, I will show you the equations of the kappa. Yeah, but roughly speaking, that is that effect. Okay, so I think this is the results I want to show you today, and there is some kind of summary I want to finish. So first, why transmon superconducting qubit is good. It can probe several areas unexplored yet. So first, we relied on the interaction between the capacitor and electric field induced by dark matter. So it gives a good values of eta, which is the effective coupling to the end. Surely you can do the same thing with the LC circuit because we just use the capacitor here. So you can create LC circuit with the same capacitance. It will give you the same coupling. But in the qubit case, we also have different things. I mean, compared with LC as well. Apart from these aspects, for example, because qubit just have two states, we can manipulate its state and use quantum enhancement more conveniently. We can tune transmon qubit gap, very convenient. And we also get this is a good one, I think. We hope we get benefits from the rapid growth of the quantum computing technologies, which mean that so the values that I used to plot the projection is some typical value in the present time. We hope that values get better in the future by the growth of the quantum computing fields. So I think this summarizes a kind of why we focus on this qubits type. And the other summary here, the true summary is this slide. So coherent wave-like dark matter such as axion dark matter or hidden photon dark matter can excite qubits, resulting in a detectable signal. And transmons, as we have seen, has good, I would say, sensitivity and be able to reach unexplored parameter regions of axion DMs. Actually, it can reach of the case of hidden photon as well. I just didn't show you yet. And if I have time, I might show you that. And the other one is that enhancement with cavity effects and quantum circuit is possible. And even reaching QCD axions maybe in the future. That's it. Thank you.
So here you have a three frequency, axion frequency, and the frequency determined by the gap of the ground state and excited state, and of course a cavity frequency.
That's right.
So you use a resonance of the first two frequency.
We use a resonance between the axions and the qubit. Yes.
Yeah. But don't use the cavity resonance because maybe it's difficult. So where is cavity frequency the setup you consider in this x-axis, for example?
Where is the cavity? It's not unique. I mean, you can take cavity frequency to be this or that. It has several modes, and those overlap between those mode function and the signal would give you the kappa factor. So if the kappa factor is reached your quality factor, if it reach 10 to the power of 6 or 10 to the power of 8, it gives you the cavity resonance. So for example, in the case of kappa equal to 1, you just don't care about those resonance with the cavity. In this case, you may have to a little bit care of the resonance effects of cavity, but it's very far from the resonance of the cavity because it's just 100. Yeah.
what happens if you choose that is a cavity frequency to be in between 10 to minus 5 and 10 to minus 4 electrons?
You mean between these?
Yeah,
you get some. Yeah, you will get some peak by that cavity resonance as well. For example, in that case, it's quite difficult. Not difficult that much. The things that happen is that you not have just qubit state and cavity state. What you got is the hybridized state or the full mixing between qubit state and cavity state. We did analyze those kind of situation in the paper. It's not that difficult, but it's different. It's kind of different behavior than I've shown you here. Yeah. But what you get is the peak.
I see.
Yeah.
So you're gaining, let's say, I try to understand, so let's say ADMX,
Okay.
and they are, of course, they are scanning the cavity frequency. Okay. And they have a higher quality factor.
Okay.
Right. There's also some resonance enhancement because of that, and the readout is just they're looking for photons.
Okay.
So I'm just saying, well, what is your what is this? So but you're proposing that they're using some qubit as a readout, and
it's
what do you gain for the most? I understand that you argue this is easier to change it. Yeah,
I think it's a little different from the ADMX in the sense that in the ADMX you use resonance of the cavity.
Yeah.
In this case, we just roughly speaking, we use direct excitations of the qubits. We can just forget about cavity and its excitation of the qubit. And of course, you can use qubit as a readout sensor for the ADMX experiments, for example. You might be able to do that. But this, we imagine a little
I'm
bit
just
different.
wondering, what is the gain? What is the
for example, compared with the ADMX, right? Okay. So first, if you just let's see the dark green one. Yeah. And this is, for example, some ADMX experiment will be around here, I guess. So you can see that as a matter of fact, in the present values that we input for the transmon is a little weaker than it.
But they probably integrated a longer time than 15.
That makes sense. But even though we increase to 10 years, I would say it's the gain from the time is not that much because it's kind of, the scaling is very bad for the measurement time. So even though you 10 years, it will not change that much. So I would say that if you use just one qubit, the sensitivity you can get is a little weaker compared to cavity haloscope experiments. That's a fact. But that is for the, given you use just one qubit and you use the present parameters of the transmon in present time. But what we get instead when we use qubit is that we get the more freely in the tuning. So we have tunability, and we also have the ability to entangle qubits or use quantum enhancement to improve our sensitivity to compete with that experiments. I think this is the comparison I have in mind.
I see. I see. So, but for the qubit readout, there's this transmon. There are something, right? Well, what are they made of? They still have to be in the cavity.
That's right. Okay, good question. I forget
5 Tesla magnetic field.
Yeah. That's also a very good question because actually transmon or superconducting qubit is known to be quite fragile to the magnetic field. But recent results by the present research that we have known, there is a direction. So for example, you have transmon. There is many directions that you can apply magnetic field. There is a direction respective to the transmon that it is less sensitive to, it's least fragile to the magnetic field. And we can add up to 1 Tesla or 5 Tesla by the present record now.
Yes. So how do you make a transmon?
And this is the figure I didn't show you yet. It's the example of the transmon from the ICPP or the International Center of Elementary Particle Physics, I think. So 3 of our collaborators who are experimentalists give us this figure. So this is transmon. So you have two pads, aluminum pads. It acts like a capacitor. And at the middle of it, the very middle, you will see something like this. And you will see something like this in the 100 nanometer scale. So inside this, you get a thin insulating layer of aluminum oxide. So this is Josephson junction. So this entire will make a circuit that I've shown you at first. And this is inside the cavity. For example, you can put it inside conductor shield. This is just example of the experiments. And you put it in the low temperatures environment to do the experiment.
Because I know that, I'm sure you know that there are some people at Fermilab also thinking about using qubit to read out photons. They rely on different technology, but one of the big thing is they don't have the qubit in the cavity.
Sorry, they don't have.
They don't have the qubit in the cavity. They are in somewhere else. And,
I see.
They need to transport the photon.
I see. Yeah, you can do that
by a meter or something.
I see. I think, for example, I see some papers that you put your superconducting qubits elsewhere because you don't want to apply too much magnetic field to them.
Because of the problem.
Yeah. But you connect some coaxial cable to transfer the signal from cavity to the qubit to read out. There is also the possible way like that. But because we going into the other way by the record that I have said to you that maybe 1 Tesla or 5 Tesla may be larger than that is applicable. So, and that direction is the direction parallel to the plane here. The transmon will least fragile to the magnetic field.
Okay.
That's it. And yeah, I think that's the thing and this is a kappa factor. So it's this one. EM is a mode function, and B0 is you apply magnetic field. So the meaning is the overlap between these two. Yeah. Okay. Thank you so much for listening. Any other questions or?
Sorry, maybe I didn't get this. What is the T1 and T2 kind of your qubit that you assume in this calculation? And what does the 15-second measurement time for each being made of?
Okay, so for example, in this case, we assume T2 to be 100 microseconds, and we assume it to be the same order of the dark matter.
Yes, you need to drive the Rabi frequency large enough for it to be seen, right?
Sorry, again, please.
Oh, sorry. So, because I assuming that the electric field from the axion dark matter is weak enough, so it takes longer time for it to drive the Rabi drive the Rabi oscillation for the population to be seen.
That's right, because the coupling is very small. So what you get is not a full Rabi oscillation.
Yeah.
We just get what we can get by that time, 100 microsecond around.
Okay, and then your T2 time is also around 100.
That's right. The real qubits that we have right now may not be 100. That's our secret now. But the one that we assume in the plot is 100 microseconds. So you repeat these kind of things by the 15 seconds allowed. So you divide 15 seconds by 100 microseconds to see how many times we repeat those kind of experiments for each bin.
Okay. Yes. Yeah, thank you.
If there are no more questions, let's thank our speaker again.
Are you still here next couple of days?
Yes.
Okay, maybe we can chat.
Thank you.